Good afternoon, everyone. I think it's time to get started. I want to say welcome, and that I'm delighted to have the opportunity to welcome Professor Sir Michael Pepper to the Waterloo Institute for Nanotechnology as a Wynne Distinguished Lecturer. So Michael joined the Department of Electronic and Electrical Engineering and the London Centre for Nanotechnology at University College London as the Pender Chair of Nanoelectronics in January of 2009. Prior to moving to UCL, Dr. Pepper had a distinguished career, first as a semiconductor researcher at the Plessey Company, and for 35 years at the Cavendish Laboratory, Cambridge University, where he pioneered the study of low-dimensional electron gas systems and the associated quantum effects. While at Cambridge, he started a long collaboration with Sir Neville Mott, who won the Nobel Prize in Physics in 1977, using semiconductor devices to investigate fundamental physics. So Michael founded the Semiconductor Physics Research Group at the Cavendish Lab in 1985 and was appointed Professor of Physics there in 1987. In 1991, he was appointed Managing Director of the then newly established Toshiba Cambridge Research Centre, now known as the Cambridge Research Laboratory, CRL, of Toshiba Research Europe. And since 2007, he's been a senior advisor to the company. In 2001, he co-founded TerraView, a company formed to commercialize the terahertz research work of CRL, and was appointed scientific director to that company too. So Michael has been associated with many of the major themes of condensed matter physics. For example, he was one of the 3 authors of the first paper announcing the discovery of the quantum Hall effect, and with his group, he developed the techniques of electrostatically modifying a 2D electron gas to form one-dimensional and zero-dimensional systems with many associated discoveries, such as quantization of the conductance of ballistic 1D electrons. So Michael was elected a Fellow of the Royal Society in 1983 and a Fellow of Trinity College in 1982, and he added to that a Fellow of the Royal Academy of Engineering in 2009. He has been awarded the Hughes Medal and the Royal Medal of the Royal Society and the first Mott Medal of the Institute of Physics, as well as the Guthrie Gold Medal and the Europhysics Prize of the European Physical Society. He received a knighthood in 2006 for services to physics, knighthood from the Queen for services to physics, and has received several honorary degrees and given many named lectures, including the Mountbatten Memorial Lecture and the Royal Society's Bakerian Lecture. At UCL, Sir Michael will focus his activities on semiconductors, nanostructures, fundamental terahertz technologies and their applications. And the title of his lecture, Semiconductor Nanostructures, reflects his interests. So please welcome Sir Michael Pepper, but before we do, just let me add that there is a reception in the foyer outside this lecture hall after the lecture. So please welcome Sir Michael Pepper.
Thank you very much for inviting me. It's a pleasure to be here. And what I'd like to talk about are really semiconductor nanostructures to give really a somewhat selective, personally selective idea of the state of the field. And I've subtitled it The Engineering of Physics, because if one actually looks at condensed matter physics, then over the past, I guess, since 1920s, 1930s, essentially the field has moved on from the study of basic crystals, naturally occurring crystals. Early work on the metals actually used large crystals of copper, which were just dug up, and to move on to semiconductors, which were artificially modified by incorporation of impurities, to move on to the study of 2D electron gases using silicon MOSFETs, on to much more sophisticated structures now using various techniques of lithography, which I will describe as we go on. So I've called it the engineering of physics because essentially it's not really the physics of naturally occurring systems. We're actually modifying and manufacturing systems to exemplify new points from physics. Hence I called it the engineering of physics. Now, there are practical reasons actually why one should go into the field of nanostructures, and one of them is exemplified by Moore's law. Okay, so Gordon Moore proposed this in 1965 as something which he'd just looked at and found empirically that the complexity of minimum component costs has been increasing at a rate of roughly a factor of 2 per year. And the number of transistors on a chip doubles every 2 years, and minimum feature size actually changes by this amount. Now, the surprising thing was that he thought this would make a nice overhead for a conference talk, but in fact, since this time, it has continued to hold, which is quite remarkable, really, because you can't think of many theories which survive over 40 years, completely unmodified. And the consequences of this are something that I'll look at now. This actually is what this has come to be known as Moore's law. And you can see there the relationship, logarithmic relationship, which is actually starting just to break down now, to break down not for any subtle physical reason, as was always thought, but for more practical reasons, which we'll come on to in a minute. But you can see actually different types of device from different manufacturers, how actually it actually holds. So this is Moore's law. Now, here's the implications of it for physics. SIA is the Semiconductor Industry Association roadmap. They actually draw up roadmaps of how they think the industry is likely to develop in the future in order to give people some idea of what to work on and what to investigate. It's very much their personal opinions, but they're usually pretty near the mark. You can see the historical trend there, which is what we call classical. In other words, classical physics as opposed to quantum physics. Quantum physics in this instance meaning that one has to take into account fully the wave nature of the electron, whereas with the classical age and classical physics, one can make approximations to the particle concept. And you can see actually here the number of electrons per device. We start off with sort of 10,000 there. And basically we come down all the way. So this is the size of the chip, the number of transistors on the chip, 16 gig. And essentially here we hit a brick wall when we get down to 10. Because a number of factors arise then, not just the quantum aspects, but the fact that one can no longer average. When we measure samples, essentially we average. And if the samples are extremely small, we can no longer average. And this is the economics of semiconductor manufacturing. I mean, it's quite sobering, really, because we take into account all these advances in semiconductors, mobile phone there going off. We basically assume that this will continue. But you can look at this. This is the cost per billion. Up there, at the top, we've got the world economy. Going up at that rate. That was basically the rate of growth of the world's gross national product. And there you can see the electronics market, which by the year 2020, if nothing happens, and of course it will happen, it's going to converge with the world economy, which means there is absolutely no resource for anything else apart from making electronic devices and using them. And not long after, the semiconductor market will then take over the electronics market. Similarly, you can see there, all the way down to DRAMs. So basically, something will have to occur in order to actually take over. So if we want to have continued progress in electronics and semiconductors, obviously new technologies have to come along, which are cheaper. Which is why there is interest and funding for semiconductor nanostructures. And of course, there's some very interesting and worthwhile physics in it as well. This is the cost of the plant, which of course is just embodied in the previous view graph I showed. You can see rising very rapidly. That's the cost of a fabrication plant. Doubles every 3 years. So by 2035, we can't afford to actually even make one plant. So you might say, why do we have to do this? Why can't we just make devices smaller and smaller, as has happened in the past? In other words, can we not scale transistors? Well, actually, it's not really quantum effects which actually prevent us from making them smaller at the present stage. It will in future. In fact, it is actually power dissipation. You may have read actually a couple of years ago of Intel abandoning a particular integrated circuit because of heating. You'll notice if you look inside a desktop computer, it's mainly space. There's a fan and space. That's to get rid of the heat. That's why laptops will never be as fast as desktops, because you can't get rid of the heat. And this figure here illustrates power dissipation. Here's the power density against year. This is actually, these are the circuits here. So it's not too bad. This is a typical hot plate in a lab, which I guess is about 100 to 200 centigrade. That's the power which that plate will dissipate. I guess something which is the order of 6 to 9 inches in diameter. That's a nuclear reactor there. That's a rocket nozzle, and that's the sun's surface. So you can see actually the projected rate of development of circuits means that we're more or less there. And which is actually a reflection of reality. You'll have noticed how hot transistors do get and the circuitry gets. And this is the problem. This is what is going to limit actually the increase in performance, increase in complexity, and miniaturization. Hence, there's a search for new technologies, and it may well be that no new technology comes along. Basically, the motor car engine hasn't changed very much in the last 40-odd years. There's introduction of electronics, introduction of fuel injection, but it's not really dissimilar. Aircraft haven't changed their fundamental design, actually, since World War II. They've just got better, smoother, more efficient. So there's no reason, actually, why a new technology should come along to take over from the existing technology. It may be that the future is software, but it may not be, and that's why there is considerable interest in actually looking at new technologies, and the semiconductor nanostructures I'm going to describe would be one. Now, in terms of the science, what is one of the problems which one will experience? Well, it's just this. That here you can see, here we just saw, it's an electron micrograph really, of polysilicon as a gate, silicon dioxide and silicon, of a sort of standard device. But there are fluctuations, and as devices get smaller, we can no longer average. So you know, one's accustomed to talking about semiconductors of 10 to the 15, 10 to the 16, and so on, dopants per centimeter cubed. But if you're down to a sample which is so small that even at this level of doping, the total number of impurities is, say, 10, then their actual topology and distribution affects things. So you have to go beyond specifying average quantities. Indeed, average quantities don't actually tell you very much when you're that small. This is the so-called mesoscopic regime, which is intermediate between the macroscopic and the microscopic. Here we have basically what happens. Now, at the moment, of course, this is an effect which is confined to low temperatures, because we're talking about quantum interference as a limiting feature of resistance. And what quantum interference is we consider the electron as a wave, and the wave comes in and it's scattered. And it's scattered actually by every impurity. And so we can get the situation where the wave comes around and interferes with other waves. And this gives rise to a contribution to resistance, which is actually random as parameters change. The next slide, this actually shows what happens. This is an experiment as a function of magnetic field. That's resistance, and this essentially is a low temperature measurements. But you can see the fluctuations there, and these are real. They're quite reproducible. You go backwards and forwards, and you'll notice even in the absence of the field. So say we take a constant field. As we come up now, the resistance is changing in an almost arbitrary manner with the gate voltage. Now, that's an example of what happens because we have so few impurities in the system that we can have two samples, one with 10 impurities in it, the other with 10 impurities in it. The distribution is different, and the resistance and the behavior of the resistance as a function of carrier concentration will be quite different because we can no longer average. The topology of the distribution of impurities determines. And that's the mesoscopic regime. Hence, there is interest in going beyond that going towards the nanoscopic regime, in which we get rid of impurities completely. And that's an interesting topic which I will be coming on to. Here we see, this is the so-called RTS, random telegraph signals. And this is what happens if you take a small piece of semiconductor and you just look at the resistance as a function of time. This is a fairly arbitrary unit. This is a fairly arbitrary unit here. But this is what happens as a function of time. It fluctuates like that. And what that is caused by, every semiconductor will have some defects in it, some impurities, some traps, which will just charge and discharge. If we take a macroscopic piece of semiconductor, say something which is, I don't know, macroscopic in this context, can be as small as 10 microns square. If you take one of those, then you won't see anything. It's constant as a function of time. If you have something which is very small, then a change of occupancy of one trap, one electron going in and out of a trap, will change the resistance markedly. Now, we can exploit this actually in practical devices, which I'll come on to later on in this talk. But for the purpose of stability and reproducibility, you wouldn't actually think very much of this actually. Imagine that would be a semiconductor memory. It would just be changing in an arbitrary manner as a function of time. And so would your calculations. So what is after CMOS? Well, a variety of possibilities. And in the famous quotation, these are the known knowns, and they're also, if we progress, the unknown unknowns. So there will be new systems coming forward with time, of which we haven't the faintest idea, but they will come forward, that we can be sure of. Now, numerator oxides with high electron mobilities, which are very easy to make and we can put down in large areas. Spins and magnetics is a huge field on spintronics. That is using the spin of the electron, because at the moment we've only made use of the charge of the electron. Quantum data processing, making use of quantum principles, and indeed more CMOS. Basically, we just continue to make CMOS circuits more sophisticated and make the software more powerful. Now, if we go from the mesoscopic regime to the nanostructure regime, what happens is, as we make the size smaller, then we quantize. Familiar with the particle in the box, that if we actually confine a wave, then we introduce a zero-point energy and we introduce discrete energy levels. And they actually give stability to the system. And essentially, the number of fluctuations found in experiments will just decrease because the nano regime is very stable indeed. It is actually to some aspects of nanostructures form what has become known as the quantum protectorate, in which quantum principles guarantee stability and reliability. So how do we make these nanostructures? Well, the common or garden method for making nanostructures in the most popular semiconductors, which are 3-5 semiconductors or 2-6s, is molecular beam epitaxy, which is a controlled growth at atomic layer at a time. And this makes use of ultra-high vacuum. We have various techniques for surface analysis. It can be controlled to a monolayer and an extensive range of materials, 3-5, silicon, germanium, 2-6s, metals. And impurity levels can be reduced to 1 part in 10 to the 10, which is really quite unprecedented for methods of crystal growth. This is, in fact, a VICO Gen 2 MBE chamber. I saw an MBE chamber here today, and very similar to that. And you can see essentially what these sticking out are. These are actually ovens in which we put material. They're heated up to high temperatures. The vapor comes off, and within the high vacuum in there, there's a substrate on which they condense, and we can grow atomic layers at a time. That's actually a production MBE system. He's of normal height, so you get an idea of the size of the facility. This will be used in semiconductor plants to make the gallium aluminium arsenide gallium arsenide system, and these will be used for laser diodes, such as control your television set remotely, general LEDs, which are in the infrared, essential bipolar transistors, heterostructure bipolars, high electron mobility transistors. Most mobile phones will have transistors made out of this technology as the front end. The front end amplification, which because it's low noise, high frequency, low noise amplification. They will also make the modulators, which are used in optical transmission of data. So particularly in indium gallium arsenide, the laser diodes and the modulators will all be in that material. They're quite expensive, £2 million. It's actually is really where the semiconductor wafers are loaded, and then the layers are formed on top of them, and they're taken away to be diced up and fabricated. The two-dimensional electron gas can be made from this particular technology, and I don't want to actually to dwell upon it too much, but what it looks like is this. There we have a layer of N-type gallium arsenide on the surface. That is doped, actually. It forms a sort of protective layer or gate. You're familiar with gates from MOS type of transistors. Can be doped. And there's the aluminium gallium arsenide. There's aluminium gallium arsenide. And there's the gallium arsenide. Now what happens is, this is doped N-type, and the electrons from here fall down into the gallium arsenide. And this layer here is undoped completely. And what this means is that the electrons, which form a layer against the interface, they can't get back into the aluminium gallium arsenide. They don't have money. They don't have the energy. And there's a distance of several hundred angstroms between these electrons and the dopants which give rise to them. Hence, they're not scattered, so they have a high mobility. Because they have high mobility, the noise is quite low. That makes them ideal for amplifiers. And this is what the band structure looks like at the surface here. This is the aluminium gallium arsenide. There's a potential well there. And because there's positive charge in here, the conduction band at the surface comes down, and the electrons are contained in this quasi-triangular potential well. And there's distinct quantized levels, because the electron is a wave, and it suffers quantization when we confine it. This is an example, really, of the epitaxial layers, the quality of epitaxial layers grown by molecular beam epitaxy. This is a particular device structure. What I'll draw your attention to is actually the atomic planes here, which are well nigh pretty perfect, actually. You don't see much of a defect there. And that's the advantage of the system, that the aluminium gallium arsenide and the gallium arsenide are almost perfectly lattice matched. And so there's very little scattering at the interface. And because of this, the mean free path for scattering is very high. And all various types of quantum phenomena can be seen without the complexity of scattering. Now, this is an example of how one actually looks at the growth process of the molecular beam epitaxy. And here we have, this is known as RED, reflection high energy electron diffraction. A RED, an electron beam is shone at the surface of the epitaxial layer as it is growing. And what happens is, there's quite a strong reflection when we have a complete atomic layer. When we have an incomplete atomic layer, it's essentially diffuse scattering all over the place. So not very much comes back. So what happens is this oscillates as we grow the layer with time. And this is what you can observe looking through the window. There you are. You see it oscillating away. Every time it oscillates, that's one atomic layer which is grown. And of course, this actually is digitized, fed into the computer, and the number of layers is carefully controlled by the computer. And then when we've grown the requisite number, shutters come across, and one moves on to the next layer. So in this way, the whole system is completely automated. Now, there are two principal methods of fabricating nanostructures, depending really on what one wants to do. The first is to electrostatically squeeze the electrons. This is used for electronic applications, particularly for the emerging science of quantum computation. Essentially, one forms patterned gates on the surface of the semiconductor, and by applying negative voltages, the underlying electron gas can be squeezed into any particular configuration. There's also self-assembly. This is particularly the self-organized indium arsenide quantum dots. These quantum dots arise because when indium arsenide is grown onto a surface of gallium arsenide, there's a big disparity in the lattice parameter, and they form small dots. This is used for optical applications, particularly for the emerging science of quantum communications, and indeed for single photon emission, for the emission of entangled photons. It's got a number of applications. Having said that, I'm not going to consider it any further because time is short, and so I'm just going to discuss the electronic applications, which are mainly arising from the electrostatic squeezing of electron gases. So this is what happens in reduced dimensionality. If we confine a carrier in one spatial dimension at a scale of the order of the de Broglie wavelength, then we get quantum size effects. So this is bulk. This is the density of allowed electron states against energy. And it forms, basically, it just goes like that. And here we see what happens if we have a quantum well. And what we have there is, in 2 dimensions, we have a constant density of states. But every time we add a new state to this, it jumps up. So it forms this sort of pattern. Essentially, a 2-dimensional electron gas or 2-dimensional system has a constant density of states. But every time we add a new level, then we add another. So we get a step function like that. And in fact, it approximates the 3-dimension. You can see the envelope there being the same as 3 dimensions like that. 1 dimension is very different indeed. It's very strange. You get a series of levels like this. So in other words, at the lowest energy, the density of states reaches a maximum and then decreases as we increase the energy. And this is a quantum dot, which is where the electrons are quantized completely in all 3 dimensions, and you just get a series of discrete lines. And we will look at all these things in due course. So what is a 1-dimensional system? Because I'm going to discuss that now. Well, the energy levels are quantized in 2 of the 3 dimensions. That means the levels are fixed. The energy is fixed in 2 dimensions. The levels are fixed. The electron is only free to change its momentum in one direction. So it's just like a pencil. The electron will come down here, can change its momentum in response to an electric field, but in that direction it's limited, it can't change its momentum, and in that direction it can't change its momentum. A variety of examples exist. We're going to look at quantum wires, but contact between a scanning tunneling microscope and a solid. Any contact when only a few atoms wide and long makes contact. Now, the interesting feature of this, which makes it completely different to macroscopic behavior or anything else, is that the resistance, if we measure a resistance, it is quantized. And it's quantized in units of the fundamental constant of conductance, which is h over e squared, where h is Planck's constant and e is the electron charge. It always comes as a surprise to realize that that actually has dimensions of ohms. But it does. And a 1-dimensional system in which there is no scattering, transport is ballistic, has a resistance which is just over 25 kiloohms. So, just to remind you, actually, these are quantum states here. This is a potential well, parabolic potential well like that, and it's very much like the square potential well you read in standard texts in quantum mechanics. There you can see a quantized wave function. Here we see what the charge density looks like. That's a ground state, that's an n equals 1 state, 2, 3, all very standard. And basically in the direction where the electron can change its momentum, E is parabolic, E goes as k squared. So we have that particular relationship where that is the energy of confinement in the other 2 dimensions. So this is how one makes such a structure in a semiconductor. We start off with a 2-dimensional electron gas formed at the interface of gallium arsenide and aluminium gallium arsenide, as we've just discussed. We form, this is the most simple structure, on the surface, two metal gates. And if we apply a negative voltage to these two gates, we deplete the electron gas underneath. And we end up with a little bit of electron gas there, a narrow constriction, which can form a wire. We can basically squeeze it until we just get rid of it completely. So to give an example, we can squeeze it typically from about 1,000 angstroms wide down to nothing, more or less. And this is what happens. These are the levels. That's the Fermi energy there. So below the Fermi energy, all the electrons, all the levels are full. Above it, they're empty. And you can see what happens here. As we squeeze this, we narrow the electron gas, we increase the energy of the electrons. As they go through the Fermi energy, they lose their electrons. And we've shown this by the fact they change color. So they come back now. There we go. Up they go. And as they go through the Fermi energy, they lose their electrons. So we can study the transport processes of the electrons as this happens. So what the conductance does, actually, it counts levels. If we measure the conductance, and the conductance, before we discussed resistance, H1 E squared, but if we say it's E squared upon H, times a factor of 2 for spin up, spin down, then if we measure a conductance of 2E squared over H times N, that means we have N levels, and so we can count the levels. And this is what we do in the experiment. So this illustrates what happens. See, we turn this on. This is the 2D electron gas. Now the 1D region becomes high resistance and takes over, and we blow up these steps here, and that's what you see. This is a very low temperature experiment, 60 millikelvin. And that's what one sees in experiment. The jumps are 2E squared upon H. It is possible to actually apply a magnetic field and make it E squared upon H, but that doesn't change the principle of the thing. So what one can see in an experiment is up to 30 quantized levels. And that means, if you think about it, think of the nodes of the wave function. We start off with half sine, and then a sine, and then more and more nodes. We've got about 30 nodes, all of which are independent. There's no scattering in the channel, so there's nothing to mix these levels up at all. The electrons behave as if they're in resistors in parallel, completely independent of each other. Now, there are many other examples of how one can actually get a quantized conductance. Not necessarily at low temperatures either. For example, if one takes a metal wire, a regular metal wire, and we just stretch it like that, it will of course break. If we measure the resistance as it breaks, the resistance of it gets higher and higher and higher until it goes to a value of infinity because there's no contact. But just before it snaps, the resistance or the conductance goes as 6E squared upon H, 4E squared upon H, 2E squared upon H, because the number of atoms in contact, if we've just got two atoms like that, then we get a conductance of 2E squared upon H. If we have like that, then it's 4, and if we have like that, 3, 6. And you can actually see this in an experiment. You just pull the wire apart. This is room temperature, set up in the lab, and you can just see those steps on an oscilloscope. This is unfortunately, this is not very good because it hasn't come out very well. This is from a paper in which people had looked at the structure of the wires, and you probably can't make it, hasn't reproduced very well actually, but this is palladium, this platinum, this palladium, but basically just before it snaps there are filaments which will give rise to the quantized conductance, and the filaments are one atom wide, but there's a number of them, and as we pull it, so they snap. And we start to get the quantized conductance. This is an example of a gold wire from these authors here. This is room temperature. This is basically we're stretching the wire at a constant rate with time. So we plot the conductance as a function of time, 0.2.4 milliseconds. And you can see what happens. It sticks at this value, That means essentially the contact is 2 atoms wide, then we break one atom wide, and it snaps. That's another sample. At lowish temperatures, it's more stable. We can go on, actually, like that. See? Very flat, very flat. An example of a macroscopic quantum effect from a very simple system. Ted Davis at Leicester University set up a teaching lab experiment in which he took a relay switch, just an ordinary switch, brass switch. You just tap it to make a contact. And if you tap it, then as it comes down like that, the first contact is 1 atom wide, 2, 3, and so on. And when it comes away, you get 4 atoms wide, 3, 2, 1, 0, so on. And so this is what it looks like. This is just a standard metal switch. You're tapping it. You're measuring as a function of time, and you see here a quantized conductance. So it's basically fairly widely observed. This, of course, is room temperature. So any time you have a contact between 2 metal objects, or between 2 conducting objects, as they touch that contact, because when you look at the surface, of course, it's very rough. As they touch, it's 1 atom wide, and you force them together, you completely remold that surface. Indeed, there are some nice experiments where you can set up a pendulum, just a brass piece of brass there, and just another piece of brass, which just, or any other metal actually, just sort of taps like that, and you can look at it on an oscilloscope, and you can see the steps rising. And this is just a room temperature with a very primitive, cheap setup. So it's a very good example of a quantum effect which comes through. Now, what I'd just like to go a little bit further. We've seen the quantized conductance in the semiconductor. What can we do with it? Well, one of the more interesting features, something which has actually held the imagination of physicists for over 70 years, is a suggestion of Vigna in the 1930s that if one has an electron gas in a uniform potential background, then under the right conditions, this electron gas, instead of having electrons which are free to move and they move around and scatter off each other, in order to minimize their energy, the electron gas will start to form an electron crystal. The electrons will take a regular lattice position, and they will not move, they will be immobile. And that is the Vigna lattice. Now, it's very difficult to see, actually. There's only one real sighting of a Vigna lattice, which electrons which are trapped on the surface of liquid helium, but there's so few of them, they form a non-degenerate classical system. So to get a quantum system is very difficult. It's thought that the fractional quantum Hall effect might be something like that, but this is an example of a calculation by Matveev, Meyer and co-workers. Now, this is what you've got. If we take a one-dimensional system, as I've just discussed, which is a strongly confined electron gas. So basically, we're holding it like that by means of a potential which we're squeezing on the side like that. So we're holding that. Now, so the potential looks like that. The electrons are there, and they form a line going down. What happens if we relax the potential like that? They can now start to move out sideways. Of course, they basically will push up their energy, so they don't want to do that. On the other hand, they will be further apart. And of course, if the system is dominated by the repulsion between electrons and their mutual energy, if they can move apart, they will minimize that energy. So although they're climbing up the potential well there, if in fact that increase in energy is less than the decrease due to the fact that they're further apart, then they will do it. And that's what happens. You start to get a zigzag pattern like that. See electrons like that? And one of the more interesting features is, as the zigzag develops, is that this electron can be nearer this one than that one. So in other words, what was previously its second nearest neighbor there becomes its nearest neighbor. Now, as we further relax the confinement potential, so it's almost flat, what happens is this zigzag will split up into 2 distinct lines. And that is an incipient lattice. In other words, the electron gas is now starting to form the precursor to a full lattice. I mean, in a sense, the 2 lines here, or rows, is a lattice. but it's basically moving towards a full-blown two-dimensional lattice. So how can we see this? Well, this is an example, actually. This is what happens if we take a one-dimensional system. As I mentioned before, its resistance goes in units of 2e squared upon h, 4, 6, and so on. This is strongly confined, and what we're doing here, we're repeating this experiment, but we are reducing the confinement. So now it can actually spread apart. Now you'll notice what happens is this first level at 2e squared upon h has disappeared, and it now jumps up to somewhere near 4e squared upon h. That's 2 levels. So this is an example of the formation of these rows in a weakly confined electron gas when we start to weaken the potential and allow the electrons to move sideways. Further, you can get quite spectacular examples of this sort of behavior. I just want to show what happens in a high magnetic field. This is a high magnetic field which actually completely changes the energetics by lifting the spin degeneracy. The only thing I want to draw your attention to is this oscillatory behavior here, which looks very much like an envelope is like a beating. This is at a lower field. You can see it there, actually. And it becomes bigger as we increase that magnetic field. There it is. And what this is actually, this is an example of what happens when two different states become close in energy. They're moving down because we're actually allowing the electron gas to spread itself out. We're giving it flexibility in that extra dimension. So it doesn't know what is the lowest energy. It can be the conventional subband picture, like that, which we've discussed before, or it could be the direct formation of 2 rows. And what happens is it tries to form 2 rows immediately, goes into that, and then energetically it becomes more favorable to go to the conventional subband picture, and the conductance drops and then rises. And the overall envelope shape is actually like a beat. But I don't want to go into that in detail because it gets rather complex. But to give an example of the manipulation of the electron gas, which can be achieved in this way, the electrons and the wave functions can be modified really almost according to what one wishes. And it gives rise to a host of new types of physical phenomena and effects. So what I'd like to say now is, when is a spin not a spin? Because we talk about spins, and there's a whole field of spintronics. So when is a spin not a spin? Well, the answer is when the spin is indeterminate. And if you've got the electrons moving around, like that, normally, particularly in one dimension, they're like that, spin antiparallel. They form a row of opposite spin directions, and like that. Now, what happens when the electron gas is very low density? They're a long way apart. A long way apart, but they see each other very strongly, repulsion, and the exchange between the two is very weak. Now the spins fluctuate, and if they fluctuate very rapidly, what happens is, essentially there's no preferred spin direction. The spin becomes indeterminate, and one can't talk about the spin of the electron anymore. It's actually a spinless particle, because the spin can take any particular direction, does so very rapidly, and we can't discuss it. This is the so-called spin incoherent regime. And this is an example. Remember before, the quantized resistance or conductance, all it does really is it counts levels. Now, what we've got here is we're going to really reduce the density of electrons considerably until we get into this regime. So here we see the normal effect, quantization in units of 2e squared upon h, 1, 2, etc. And you'll notice it disappears, and it reappears there at e squared upon h, 0.5 times 2. Now, what that means is the basic unit of quantization is e squared upon h, but here we have 2e squared upon h, because what we essentially have is that by having a spin, we can put 2 electrons into the same momentum state. That's fairly standard work. But if we don't have a spin, i.e. we abolish spin, they're spinless, we can only get 1 electron in a desired state, and therefore the conductance is no longer 2e squared upon h, but e squared upon h. And what one can do is one can then go to very low temperatures where kT becomes very small, and then the spin coherence is restored. this can actually be, although it's very interesting physics, it can be a bit of a problem actually, because it occurs in the low carrier concentration regime at the same time as we'd like to observe a Vigna lattice. So the two effects now become rather mixed up, and one needs to sort them out. Well, there are other effects actually. What happens when devices become very small? Single electron repulsion. So if we think about a capacitor, you recall actually from student days that the charging energy of a capacitor is just E squared over 2c. But what happens when C becomes very small? Then the charging energy can become very big. And within using the facilities of nanostructures, nanotechnology, we can make extremely small devices and structures. Now, to give you an idea, if we have a capacitor which is in the floor, if we just take a small sphere and we say what is the charging energy of that sphere, then if we have a sphere of radius 0.1 microns, then E squared upon 2c, or E squared upon c, corresponds to an energy of repulsion about 100 Kelvin. So since it goes as R, we only need a very small decrease in diameter to get the charging energy to be room temperature. And this means, of course, that if we change a gate voltage on such a device, then the carrier concentration doesn't change smoothly. It basically goes in steps because the electrons are now discrete. The charge becomes discrete. Everything becomes quantized. And it's really almost a classical effect. This is what you see. This is the so-called Coulomb blockade, where one electron blocks others coming in. We have to have a resistance. In this case, it's a question of tunneling, but nevertheless, a resistance like that. It's an interesting example of the relationship between different aspects of the problem, because if the resistance is very small, electrons go through very quickly. If electrons go through very quickly, their energy levels can't be defined by Heisenberg's uncertainty principle, and therefore we can't see the difference in energy due to the charging. So you need to have a high resistance to see it. And E squared upon 2c has to be bigger than KT. But this is an example of a tunnel junction, where you see I against V, and for the first we apply V, nothing happens. And that's because we can't get the electrons on there. One electron is blocking the others. This is what it looks like. This is a silicon, actually. This is a quantum dot. I won't go into it, but basically these are all little side gates, as we've said. This is etched. It's quite a nice example of the technology. That's a line of silicon like that, doped silicon. And by squeezing the sides of it with voltages, these side gates here, we can define a dot. And if we measure the current through the dot as a function of voltage, it looks like that. Every one of those spikes corresponds to the addition of one electron. This sort of effect gave people a very nasty shock when they first started looking at nanostructures, because nobody knew what it was. People thought they had bad samples and threw them away. And then they measured again, and so they just endlessly throwing samples away until it was realized that this actually is what one should get. And that is an example of single electron charging. One can actually detect electrons, but I'm running out of time actually, so I won't go into this in detail, but what we have there is a quantum dot. Now, the quantum dot looks like this. That's the current through the dot. You see, each one of those corresponds to the addition of an electron. But if we make the dot very small, the current goes through it very, very slowly, and we can't measure it. But every time we put an extra electron in there, the state of charge through here, or if we have a current through here, which is very sensitive to the charge there. Every time we have an extra electron there, the current here drops. And this is what you see here. This is the current through the detector. And you can see how it continues to oscillate, even though we can't actually measure the change in number of electrons on the dot. This is an example of quasi-non-invasive detection of electron processes, which is very useful in the emerging concepts for quantum information. Now finally, my last couple of overheads, in case you get worried I'm going on for too long, basically is how to make use of this to measure the electron charge. Believe it or not, there is no real method for measuring the value of electron charge. after all this time and all this effort people have put into electronics, there's not really much of an advance on Millikan oil drop or shot noise. But if you look at the tables, you'll see the charge on the electron is given to 7 or 8 decimal places. You should be very suspicious of this, because what is done is to take the value of E upon h from the Josephson effect, and that E upon h can be measured to enormous accuracy, 1 part in 10 to the 8 10 to the 9, E squared upon h from the quantum Hall effect, which again can be measured to exceptionally high accuracy, and take the ratio, which gives you E. But there's no real method for the direct measurement of E, and standards laboratories would like to have this. And it's not just that, but we would like to have systems where there is a controlled number of electrons which can be transmitted. So one can make use of the Coulomb blockade type of effect. This is an example. You might not think so. This is an example of an electron pump. Here, as you can see, this is actually 500 nanometers. So it's pretty small. Remember, 500 nanometers. Remember, human hair is about 100 microns. So human hair will be much greater than this wall, something like that. And there you see, actually, this is doped gallium arsenide here with electrons in, and these are gates across it. Despite their rough appearance, they work very effectively. And what we can do is we can actually pump electrons by means of varying the potential on these gates. We can just pump them through like that. And this is what it looks like. This is the pumping mechanism here. See, its potential goes up. The electron tunnels through there. This potential comes down, and the electron comes in. Whoop, up it goes. And now, there it goes. Now, the thing is that we can't get more than one electron in because of the repulsion, the Coulomb blockade between electrons, means we have 2 of them. But to get 2 of them in, we have this amount of energy, and we can't get that amount of energy. So therefore, we control it to 1. So we can pass 1 electron through at a well-defined frequency, and the current is just charge times frequency. This is what happens if the frequency is too low. The electron can actually whiz out that way, as well as that way, which of course means we have an error. Here it goes, look. Comes in, it's there for a long time, and look, it can go that way or that way. In fact, it can go that way quite easily, and it's gone. It's gone that way, it's gone back. Here the frequency is too high. So basically, there's a certain probability of tunneling through, and it can't do it in the time. It's much too high, so that gives us an error. So if we have the right sort of frequency, then we will get a well-defined charge which goes through. And this is what happens. This is an example of quantum pumping of single electrons. And this is basically the current through is EF, and this is actually what we would expect if we take the standard value of charge from the ratio of quantum Hall and Josephson. And this is the error. It's about 1 in 10 to the minus 5. In fact, more recent pumps actually are better. So this is an example of how one can actually exploit the Coulomb blockade. And one can go a bit further than that. One can actually start to make all sorts of rather sophisticated experiments here. This is a ring structure, there's a pump, and this is a beam splitter. You see, because the electron is a wave, we can actually have all sorts of optical analogies here and study a variety of interference and diffraction effects. This is an example, again, you can see it's quite nice. That's 5 microns there. So you can see the sharpness of the lithography on a scale much less than a micron. And so this is the future of nanoelectronics, a particular area of nanoelectronics, looking for new effects which might form the basis of systems of quantum data handling and quantum computation. And on that note, I'd like to thank you for listening and thank you for inviting me.
Mr. Michael would be prepared to answer questions.
Sure.
How far are we from real systems working in computers? It seems that the time is flying because you say that the money required will hit the wall. So from these systems, from these properties, how far are we from being able to combine them and develop a real logic that could be helpful for computers?
Well, quite some distance, actually. Quite some distance. I mean, the field does move fairly rapidly, but at the moment one can't actually specify anything. I mean, it's very promising. Quantum operations have been performed and observed, but to actually have them as a real computational system is a long way away.
Thank you very much for a very exciting talk. I'd like to ask you, under what pressure actually is one-dimensional quantum gas exists? Because you said something about milli-Kelvin, so must be, what's the pressure?
The temperature.
I mean, the temperature is milli-Kelvin, but what's the pressure?
The pressure?
Yes.
Well, I mean, normal. I mean, basically, well, they're held in vacuum, but I don't think, or else, for some experiments, they're immersed in liquid helium, or liquid helium mixture, yeah.
Because I think it has to be very low.
Yeah, I mean, they're fairly robust, actually. I mean, pressure, if you apply pressure, then, of course, you can alter the band structure, but we're a very long way from that, actually, yeah, essentially.
Thanks so much for the interesting talk you enlightened us with. My question actually is regarding the definition of the Mesoscopic regime and the Nanoscopic regime, and why I understand the Nanoscopic regime being trying to avoid all these noises, all this scattering, but still I don't see the definition. Why nano? Still, why not angstrom regime? Why not? Why this dimension? And the other question is about tunneling. The problem with quantum mechanics is that we don't have control much, and we rely on statistics, mainly averages, the observables of all these things. Now, what do we do if we go like on individual subatomic particles like electrons and so forth? Thanks.
In a sense, the question of averaging is the problem in the mesoscopic regime. So we try to avoid it by going straight down to the nano regime. As to what is a good definition of it, I mean, it's just very loose, actually, because in a sense, to talk about the sort of phase locking of electrons and the elimination of fluctuations depends upon the number you've got and temperature and so on and so forth. And of course, the higher the temperature, which is what you want, the more restrictive the nano conditions. So you find you've got to squeeze the device smaller and smaller. But typically, I think if one started to work of the order of 100 angstroms, then one will be well and truly in a nano regime at room temperature. Well, you are in room temperature because essentially the FETs, which work in mobile phones, or the modulators, which are used in optical communications, they are room temperature, and there they work on the basis of quantum wells, producing quantized levels. So modulators will work on the basis that a two-dimensional exciton will have a higher binding energy than a three-dimensional exciton because you're forcing the electron and the hole together. So, you're talking of order 50 to 150 angstroms, around about 100 angstroms or so. But of course, if you go down to very low temperatures, then your length scales become bigger because you can work with energy levels which are much closer together. So, I mean, that's perhaps not a satisfactory answer, but there isn't actually any real definition. It really depends upon the conditions. But there's an objective you wish to achieve, and once you've achieved that objective, you're in the nano regime.
What about the statistical aspect of the quantum mechanics? Once we get into the nano regime, so what do we do about that? What are the tools, the theoretical tools that we handle this kind of regimes?
No, I mean, well, for example, you can use the transmission of electrons or photons through a barrier, which is as a random number generator. If you've got a sort of if you've got a beam splitter, either for electrons or photons, either way, then essentially, if you just monitor the output, that's a random number generator. So it actually is used in quantum communication circuitry for the generation of random numbers in the communications. So essentially the thing to do is to accept it's there, know it's there, and make use of it.
Yeah. Okay, I was considering if we have a semiconductor material like silicon, and we want to make, we consider one-dimensional problem. So electron associated with this, suppose 1 nanometer silicon, like it will have, if we consider this problem as a particle in a box, so we have energy levels which are 1 over L square with inverse proportion. So if we increase the length of this specimen, then energy levels they condense. So is there a workable length on nano scale which will be better to make devices?
Well, again, I mean, it really depends upon functionality and what you want from them, and the overall condition, number of carriers. Yeah, I think you always come back to the 50 to 150 angstrom mark. If you want to modify, let's say you want to modify the exciton, then the Bohr orbit in silicon is typically about 20 angstroms. So you've got to work on a scale which is, well, the wave function decays exponentially, say 30, 40 angstroms. Gallium arsenide a bit bigger because everything's bigger. So it depends upon the effects you're after, but take the Bohr orbit, that should give you a rough idea. It's quite interesting that particular point, because there are ideas on the fact that in 1D everything is localized. Because you've got scattering, so if you've got a number of scattering centers, then electron cannot escape. It will actually eventually, if it's infinitely long, be sent back to the origin. That's known. Polya from classical diffusion and Mott in quantum. So if you actually reduce the length scale, then you come to a region where you get a maximum metallic resistance, because essentially it depends really on how rapidly the electron moves through. Because if you've got quantized levels, and let's say every x they move around because of scattering, that distance x determines a sort of classical resistivity. But if they go through that very quickly, then basically the uncertainty of the energy, h upon t, can be greater than the mean level separation, so they don't know that they're actually in quantized states. So that is an example of the length dependence which you're referring to, I guess. But it overall just depends upon the phenomenon you're after, the length scale. But
what have not been done on any specific material in this?
Well, specific materials, well, people looked at silicon and a variety of 3-5s. And essentially, then the effects are all there, but the length scale changes. So the conditions become more, in silicon, the conditions become more arduous than in 3-5s, because in silicon, the mass is bigger, so the quantization is less, and mean free paths are less. So you have to work a bit harder to achieve the ends. But yeah.
Thank you.
Thanks again. Actually, I just remembered the question that I wanted to ask you. It's actually even at the quantum mechanical state where you have all the nano regime. Like, for example, the tunneling. Still, we are talking about statistical here, because we say probability of going like the switches that, like the pop.
That's exactly right. Yes.
We still cannot avoid fluctuation because it's an inherent nature of the subatomic particle here.
That's correct.
In the electron, for example.
That's correct.
So, still, fluctuation is there, so can we...
That's correct. No, I mean, you're quite right in the pump. As you say, I mean, the earliest pump was called a turnstile device, in which essentially it made use of tunneling, complete use of tunneling, and it failed above 10 megahertz, because the time constant for tunneling basically was over the order of a few microseconds, and therefore once you got more than a few megahertz, then the time constant and the averaging, would actually, part of the time, the electrons wouldn't tunnel. So gradually those plateaus became slopes. It wasn't a sudden disappearance, because as you say, it's statistical, but gradually, as you increase the frequency, a plateau became a slope and then disappeared. Yeah.
In your slide titled Beyond CMOS,
You mentioned turning to things like metal oxides with very high electron mobility.
Yes.
Are these things like molybdenum dioxide, or could you expound more on that and what benefits these would convey?
Well, it's actually horses for courses in a way, because I don't think these materials would be used in, say, for computation, because they're still too slow compared to silicon. But if you want wide areas, as you know, over the past there's been a lot of discussion about the use of organics, because you can put them down very easily, wide areas, and in principle cheaply. In principle, it may not be in practice, not the case, but in principle. Now, in fact, the reliability is dreadful, and the mobility is so awful that they have high resistances, and it's not really such a viable technology. But you can do with these oxides what you'd hope to do with the organics, and get electrical properties which are a factor of 1,000 better, because you've got mobilities of 60 to 80. And you don't have the reliability problem. So if you want a sort of wide area electronics, for, say, throwaway electronics, something like that, for screens or whatever, where you're not too worried about overall computational speed or lifetimes of 10, 15 years, then they would actually fit the bill completely, and in principle they could be very cheap. So it would be that, actually. And maybe it is possible to get them to a higher mobility, and then maybe. I don't know. But basically, people are looking at them for that particular function, which was envisaged some time ago for the organics, but the organics basically don't have the right performance.
Any other questions? Yes? Go.
I have a question about the single electron pump. So what is the co-tunneling rate, and how does that compare to your former solvent device?
Yeah. That's quite a difficult question to answer, actually, because I'm not aware of any measurements that we have done on the co-tunneling in these systems. Perhaps if I can dodge the question and talk in terms of errors, because co-tunneling would give an error. Yeah, I mean, basically there will be phase slippage. In other words, the electron would tunnel when it shouldn't tunnel, and so it will be wrapped up into the error. What is interesting is if one does look actually at the difference between the measured value and the accurate value that you'd expect from knowing E, from Josephson and quantum Hall, you don't actually get a value above it. It's always below. So now if you blow up the plateau enormously, it's always like that, as if in fact every now and again an electron doesn't come in, or it comes in and it goes back. Yeah. But the co-tunneling, that, to the best of my knowledge, it would be very difficult to actually isolate it in such a system without, maybe if one had detectors around, then they would have to work at this very high frequency. It's very difficult to do.
Other questions? And I'd ask you to join me in thanking Sir Michael for a very insightful talk on some of the fundamentals of electron behavior at the nanoscale. Thank you very much. There's a small gift.
Oh, thank you. Thank you very much.